background information and specific characteristics of the sensors I used. Then I'm going to talk a little bit about the Kalman filter, which is the data processing algorithm whose effectiveness we test. I'm going to detail the design and construction of a test platform I used to test the effectiveness of the Kalman filter. I'm going to show my results and talk a little bit about improvements and future work that can be done on this. The first bit of background information we need to talk about is the Euler angle. So the Euler angle is how we mathematically represent the angular orientation of an aerial vehicle. The Euler angle is a three-dimensional vector with one component representing rotation around the x-axis, which we call the roll component, one component demonstrating the rotation around the y-axis, which is called pitch, and the third component demonstrating rotation around the z-axis, which we call yaw or heading. The next bit of background information is about the specific sensors I used in this project. For most low-cost applications, they use what are called internal measurement units, or IMU sensors. This is the specific sensor I used on the project. IMU sensors are basically a combination of three sensors. They have a gyroscope, an accelerometer, and for indoor applications, either a magnetometer or a compass sensor, and for outdoor applications, a GPS sensor. Since this is a mainly indoor application, the IMU sensor I'm using has a magnetometer. Let's look a little bit more in depth at the gyroscope, the first sensor in the IMU. So gyroscopes measure angular velocity around each of the x, y, and z axes. So to calculate the Euler angle from gyroscope measurements, we have to follow two steps. First thing we need to do is integrate these measurements with respect to time, so we get an angular displacement from the angular velocity. The second thing we need to do comes from the fact that the Euler angle has to be in with respect to a global frame. These angular velocity measurements we get from the gyroscope have to be, they're in what's called a body frame or a local frame, and this is the reference frame of the actual craft. These things need to be, these measurements need to be transformed into the global reference frame, and the integration and the global reference frame transformation can be modeled by this equation, equation 2, right here. So the gyroscope sensor is not perfect. Here you can see I've graphed each of the components of the Euler angle over 100 seconds for a stationary sensor. And we can see that all three components drift in random directions and with random magnitude. So we can see that although the measurements have very little noise, they drift over time, and that makes it extremely hard for us to obtain accurate estimations of the attitude from the gyroscope alone. So let's see if the accelerometer can do a little bit better than the gyroscope. The accelerometer is going to measure the decomposition of the gravity vector along each of the x, y, and z axes. Then, by comparing these magnitudes and doing some trigonometry, we can calculate the individual angles on each of the three axes. These measurements don't need to be transformed into a global frame because we define the global frame with respect to the gravity vector. The gravity vector is measured by the accelerometer, it's already in the global frame. However, since the gravity vector is parallel to the z-axis, any rotations we do around the z-axis cannot be properly measured by the accelerometer. We can't get any useful information about yaw or heading direction from the accelerometer, so our Euler angle consists of only roll and pitch components. The characteristics of the accelerometer are different than that of the gyroscope. The measurements from the accelerometer do not drift over time, but they have significantly higher noise. This is a significant degree of noise that makes it hard for us to use these estimations from the accelerometer. Let's see how the magnetometer does. The magnetometer is similar to the accelerometer. It'll measure the decomposition of Earth's magnetic field across three different axes. Now, while it is possible for us to calculate a full three-dimensional Euler angle from the magnetometer, for this application in the Kalman filter, we actually only need the yaw or heading axis, which can be calculated with this equation. The magnetometer's characteristics are very similar to those of the gyroscope. Over time, there's very little drift, but there's a significant degree of noise, which makes estimations from the magnetometer also not useful when used alone. So we've seen now that none of the three sensors in an IMU can individually properly estimate the attitude of a system. This means we need to employ some sort of sensor fusion, where we combine measurements from each of these three sensors with the hopes of getting one estimation that is low in noise and low in drift. One such algorithm we can use is the Kalman filter for sensor fusion. The Kalman filter has two steps. In the first step, we're going to calculate two full Euler angles.